We have another way of determining whether a critical point is a maximum or a minimum, and the key is to look at the concavity of f at the critical point. If our point is a maximum, then the function should be concave down. Conversely, if our point is a minimum, then f should be concave up. That's our intuition, but let's pull it all together with a theorem. Suppose that f is twice differentiable and that c is a critical point of f. If f double prime of c is greater than 0, then c is a minimum, corresponding to the case where f is concave up. And of course, if f double prime of c is negative, then c is a maximum, corresponding to the concave down case. Now, if f double prime of c is equal to 0, there is more to say, but it becomes a little bit more tricky. In that case, we'll take k to be the smallest positive integer for which the kth derivative is non-zero at c. If k is odd, then c is neither a maximum nor a minimum. While if k is even, then we look to parts 1 and 2 and use the same criteria there, namely a positive derivative gives a minimum, while a negative derivative gives a maximum. Let's start off with a nice function. Let's find and classify the critical points of e to the x squared minus 2x. First things first, of course we have to find the first derivative, and using the chain rule we get this. Now the exponential is never 0, so the only critical point occurs when 2x minus 2 is equal to 0, or namely when x is equal to 1. To use our theorem, we need to compute the second derivative, which requires both a product and a chain rule, but this isn't too bad to work out. Now all we do is plug in our critical point. Once again, the exponential is always positive, and 2 is also certainly positive, so by the second derivative test, the point x equals 1 is a minimum. Next up, I'm going to do an example which actually shows you that the second derivative test isn't the greatest result. Let's find and classify the critical points of x over x squared plus 1. As before, we're going to differentiate to find the critical points. A quick application of the quotient rule and some nice cancellation gives us the following. The numerator is 0 when x is plus or minus 1, so those are our critical points. But the second derivative ends up being a total mess. Again, it's just the quotient rule, but there's a fair bit more algebra required this time. You can work this out too if you like, then skip ahead to see the answer, or you can work through it with me. Either way, it's just mostly algebra at this point. Whew, okay, finally. So let's throw our critical points into f double prime. Again, a little bit more algebra, but this time it's mostly evaluating a computation, and we get positive 1/2. The calculation for x equals 1 is almost identical, giving negative 1/2. So by the second derivative test, negative 1 is therefore a minimum, and x equals 1 is a maximum. So the second derivative test is another tool that we can use to classify critical points. But in practice, it can be quite messy to compute the second derivative. So for now, it remains a niche tool that we'll only allude to on occasion.